Hi everybody, I also see a couple of familiar faces from EF, so hi guys. And so I'm Radosław Zagorowicz from Epsilon research team in Ethereum Foundation. And the second person who unfortunately couldn't join the event because of some sudden personal circumstances is Paweł Belica. He was supposed to make the presentation with me, but hopefully you will forgive, and sorry for that. So today I'm going to talk about the Evmmax. So Evmmax is an extension we plan to add to the Ethereum virtual machine. And the talk consists of 3 different parts. So at first I will tell you a little bit about the EVM precompiles, what they are and how they are used, and also present what problems they make now and why we want to get rid of them, basically. The next I will present you the idea of Evmmax, what the motivation is to build it, and later also I will go a little deeper into the details of the work we did recently. As the last part of our presentation, I will introduce you to the POC implementation of we prepared inside the EF team. So let's start. But first, let's talk about what are precompiled contracts and what they are, why they are so important in Ethereum. So a precompile is basically an account which basically works as a contract, but it doesn't have the bytecode. So the way it works out is defined in the specification of the precompiles. But not in the set of, for example, EVM opcode instructions. So basically, it's the precompiles are implemented by the execution layer clients according to the specification of the precompiles. As I said, precompile is an account, so it needs an address, and there is a special address pool reserved only for precompiles. And for now, we have 10 different precompiles which are currently used, and the addresses basically start from 1 and go to the number of currently used precompiles. So, but you can see later that the number of precompiles and the list of precompiles changes in time. And moreover, because they look as a regular from the perspective of EVM, they look as a regular accounts, regular contracts. So if you need the method called in the precompile, you need to call the contract. So make a call from the EVM to the contract which implements the precompile. And here is the list of currently implemented and used precompiles in the EVM Ethereum blockchain. And probably you already know why I'm presenting this topic here on ZK Warsaw. Take a look a little bit on the list. For those who probably spent more than an hour in the cryptography, it should be already obvious that precompiles in EVM means cryptography. They implement the most advanced cryptographic functions which Ethereum needs. We can split the current precompile set in 3 different subsets. First one is the set implementing needed cryptographic hash functions like SHA-256 and the newest precompile we introduced in 2019, Blake 2 BF. The next set of precompiles implements the most important actually topic for us today, functions related to the elliptic curve cryptography. In this set, we have probably the most widely used precompile, which is Ethereum signature verification, which is called EC recovery, and also 3 precompiles related to the elliptic curve point operation like adding, multiplying, and EC pairing. Yeah, and the last one is just a group of Xbot, which I'm not going to talk about today, but just it's worth mentioning. So as you can see, precompiles or better the functionalities they implement is one of the most important part of Ethereum technology stack. So once again, precompiles make advanced cryptography available from the EVM level. But there is a lot of reasons that make the precompiles controversial, and why I will try to explain on the next slide. So at first, we always have a discussion inside Ethereum what should be added. There are groups of interest. They're pushing some changes because it will be useful for their projects, for example. Moreover, very often there is a temptation that maybe we should add one more precompile, which is much easier to implement in some external language than in EVM, if we need some additional functionality, for example. And it's really hard to add them, and sometimes it takes years. For example, Blake 2 was aped, so the proposed, in 2016, but it was introduced in 3 years later, actually. So people were promised that some functionality will be added to the stack, but they had to wait 3 years to have it done finally. But what's the most interesting is that these complicated functions are implemented by the external specialized libraries, which are constantly changing and constantly under development. So it can be a potential source of consensus and security issues. And we can find the cases in the history of Ethereum, which when this architecture put network at risk. So the last problem I want to mention with the precompiles is that the part of them are already obsolete, but they have to be maintained because they are the part of the protocol. Like, for example, Blake 2, we were waiting, as I mentioned, we were waiting for it for 3 years, it's already obsolete. So another thing which is a little bit worrying about this infrastructure of precompiles is that we have a long list of proposed precompiles, and so it means that that there is a need from the community to have such a functionality, but the way it's implemented now makes most of them almost impossible to introduce in a reasonable time. So on the other hand, introducing them all would put the network at the bigger risk than before. We think it's more than, and to summarize this, I think it's more than enough that we can see that we need a better solution for this. And here we come with the Evmmax proposal. So, as I mentioned at the beginning of this presentation, the Evmmax is the Ethereum virtual machine modular arithmetic extension. And so let's present a couple of motivation we had when designing this and specifying. One of the motivation is general problem with the precompiles I already mentioned. But another part is to make the future development of ECC related functionalities much easier and independent from the protocol development. Going a little deeper into technical details of the implementation, we define a list of most important technical motivation introducing Evmmax. At first, Evmmax allows us to implement elliptic curve cryptography arithmetic operation as a EVM contracts. So everybody of you can have its own ECC implementation and use it without any risk on the consensus and on the security of the protocol itself. We can also potentially consider implementing a standard ECC library available as a set of the cryptographically specialized contracts and libraries in Solidity or Viper, for example. Sorry, I need to take a drink. Yeah, and the second reason, second motivation, because of the better optimization or optimized implementation, we can significantly reduce the gas cost of the operation on 256-bit values. And for example, we want to have that small optimization. First, it's coming into mind. It's, for example, we won't have to push on stack modulus value anytime you want to compute, for example, add mod or mul mod, as it is now in the EVM. For most of the ECC algorithm, modulus values basically is constant during the computation of designing the algorithm. It changes not so often. Moreover, in this model, modex can be also implemented as a EVM contract. Now it's difficult to do it because mulmod opcode, which is a part of the EVM, which is used to implement basically xmod, is too expensive in gas, and it also consumes 3 parameters instead of 2 because of this constant, almost constant modulus for the time of the computation. And at last but not least, we will reduce the gas cost of cryptographic hash functions computations and ZK proofs verification, which probably should be kind of interested also, especially in this group. And the reason is exactly the same. The cost of addmod and mulmod operation is too big to implement this functionality in the current EVM. So the things even looks worst for the algorithms where modulus is bigger than the regular 256-bit word in Ethereum virtual machine. Like for example BLS, where we have the modulus which is 381 as far as a bit modulus, and the EVM, and in Evmmax it will be supported just natively. So, but so let's go a little bit deeper into the Evmmax specification. So let's talk about the opcodes we need to introduce to the EVM. First, I wanted to talk about setup X. Basically, this instruction, together with the parameters that we pass, creates the active modulus context, if it doesn't exist yet in the EVM. So every modulus context is fixed and cannot be changed after creation. On modulus initialization, it calculates additional parameters, like for example R², needed for later computation. So basically all the parameters which are reusable for all the computation and can be calculated before, pre-calculated, are pre-calculated on the initialization. And of course, if the modulus already exists, it's just switch the context of the computation to it. It will support different integers precision and different modulus sizes. And also setup X defines how many value slots. You can think about it like processor registers will be used in this modulus, and how many of these values it's enough for your newly implemented algorithm. So the second set of instructions is just instructions which are responsible for communication between Evmmax context and EVM context, and it's storex and loadx. They are used just to move values between the memory of the Evmmax context and the memory of EVM. They are needed to for example, if you want to transfer the computed results from the Evmmax to the EVM and use it, or you want to pass the parameters to the arithmetic functions from the EVM. So basically that's it. But they have also one more additional thing which is important. During storing, when the values are stored X or load X, they are also converted from Montgomery and to Montgomery form. So which is also important later in the computation, and it's totally opaque for the EVM from the EVM level. And last three instructions are just typical modular arithmetic instructions, which perform the computation according to their names. I think I don't have to go into details what they really do. Yeah, but it's worth noting that they are taking 3 parameters from the Evmmax memory, not from the EVM memory, as I mentioned before, and returning also the results to the Evmmax memory. We don't have to load-ex them to the EVM context just immediately after computation, because very often they will be just only reused in the Evmmax context, and that we doesn't need to load them back to the EVM because we don't need them. So to summarize, we have 3 sets of instructions. One is setupx, which defines and switches between moduluses contexts or moduluses, and storex and lowx, which copy values between Evmmax and EVM contexts, and the set of 3 modular arithmetic instructions which operate only in the Evmmax context. Yeah, and the last part of this presentation, I would like to introduce you a little bit to the prototype version or POC version of the Evmmax we prepared. Actually, yeah, Evmmax API and a couple of use cases of this API. So, using the Evmmax API, Epsilon team already implemented a couple of most important functions, which are currently computed via Ethereum precompiles. We implemented EC recovery, which is used to the signature verification, points adding and doubling for BN245 curve, and EC pairing for BN254 curve. It's important to note that these implementations use only functions from the Evmmax API. Of course, there are some intermediate functions, but they also use only the API. We did it just to prove the idea that it makes sense, and this API is sufficient to replace the precompiles now. So when implement, it may be going a little bit deeper into the implementation, but not too deep, hopefully. We implemented a list of listed earlier Ethereum precompiles counterparts to use using some well-known formulas like. And for example, for inversion and square root, we generate code using @chain tool. For point operation, we use formulas from René Castello and Bettina paper linked below, basically. And for point multiplication, we use this standard Montgomery ladder algorithm, which uses add and double formulas from the point above. And what's the conclusion? And this is, I think, the most important. Basically, we are not cryptography experts, and we know about it, but it appeared that it's relatively easy to implement these precompiled functionalities using Evmmax API only. And moreover, probably here, there are a lot of people who would do it much better than we did. But the best of it is that you can do it, start implementing your own version of ECC algorithm, not waiting until it will be available as a Ethereum precompile. So if you are interested in our work, the Evmmax code base now is a part of the EVM1, so fast implementation of Ethereum virtual machine in a branch now, but the API is already merged to the master branch. And if you are interested in the technical spec and the API, how it looks, you can also scan this QR code with the URL to the latest specification of the API. Yeah. So and the last thing I want to talk, I would like to present the list of the people from the EF working on the specification and implementation of the Evmmax, and using this to the precompiled counterparts. Hopefully, you will find the topic interesting. And if you are interested of the topics related to EVM and ZK, just join our summit we are organizing during DEF CON. EVM Summit. We'll be discussing. There will be a special blog for ZK EVMs also. I think one of the most important, or the most important part of our summit. And that's all. Basically, thank you very much for your attention. And if you have any question, you can ask it now, or I'm available here till the end of this event, and also during ETH Warsaw. There will be also more members of our team at ETH Warsaw, and definitely they will be able to ask all difficult questions. So thanks once again for listening. Hopefully it wasn't too fast and it was interesting. And you don't have very difficult questions to me. Thank you.